Now we're going to use a simple reduction to show that this language B, consisting of the descriptions of Turing machines that accept something, is undecidable. Our strategy is to reduce the diagonal language to it. In other words, we'll argue that deciding B is at least as hard as deciding the diagonal language. Since we can't decide the diagonal language, we can't decide B either. Here's one of many possible reductions. The reduction is a computable function whose input is the description of a Turing machine M, and it's going to build another machine N in this Python-like syntax. First, we write down the description of a Turing machine by defining this nested function. Then, we return that function. An important point is that the reduction R never actually runs the machine N. It just writes the program for it. Note here that in this example, N totally ignores the actual input given to it. It just runs M on its own description and does whatever that computation does. Hence, N is either going to be a machine that accepts nothing if M doesn't accept its own description, either by looping or rejecting, or if M does accept its own description, then N is going to accept everything. In the one case, the language of N will be the empty set, and in the other case, it will be sigma star. A decider for this language B would be able to tell the difference, and therefore tell us whether M accepted its own description. Therefore, if B had a decider, we would be able to decide the diagonal language, which is impossible. So B cannot be decidable.